Hello everybody, welcome to my presentation on the applications of integral calculus to physics and engineering. I'm going to be covering two topics here, hydrostatic pressure and the center of mass problem. So what is hydrostatic pressure? You can think of this as really useful for deciding how much force, or figuring out how much force is going to be applied to the side of a dam. That's kind of the classic example. But first let's do a quick physics review. So what is a Newton? Some of you may remember this, but it's the force required to move a 1 kilogram mass at an acceleration of 1 meter per second squared. Okay, and what is a Pascal? Well, a Pascal, this is the unit that we use to measure pressure. Okay, and a Pascal is equal to 1 Newton force applied to 1 meter squared of area. Now what's important to keep in mind here is that pressure is equal regardless of direction. And so the pressure coming in this direction is going to be the same as the pressure coming in this direction, as this direction. It's the same all around this point here. And that's kind of what I'm trying to show over here. The pressure at this red point, is going to be the same directly across at this other red point here. The pressure, maybe this is a bad picture, the pressure will change when it's going up and down here. But at this one point, if these are at equal depths, the pressure will be equal regardless of direction of this little force vector here. Okay. So, how do we calculate force? Well, we need the pressure, like I was just talking about, times the area. Alright, so how do we calculate pressure? Well, we have a little nifty formula here, and that's rho, the little p here, which represents the constant for the density of water, 997 kilograms per meter cubed, times g, the acceleration of gravity, 9.8 meters per second squared, times depth. And we'll be measuring force here at 12 meters of depth, but this will typically change in the problems that I'll be doing. And so all three of these are used to calculate pressure, and then in order to calculate force, we just multiply that pressure by the area of the plate, and that's going to be 4 meters squared. And so plugging it in, we just have 997 kilograms per meter cubed times 9.8 meters per second squared times 12 meters times 4 meters squared. And all those cancel out. We're left with, well, they don't the units cancel out. And we're left with 468,988 newtons. So that is a lot of force, but think about it. There's a huge column of water here. 12 meters is equal to about 40 feet, alright? And, 4 meters squared, I think, like 30 feet squared or something? It's a lot of water. Okay, so now we have our first problem. Due to extreme boredom, you decide to build yourself an aquarium for your grandfather's tropical fish collection that he wants to get rid of. He tells you the dimensions of the aquarium should be 5 feet long, by 2 feet wide, by 3 feet deep, so that the fish have enough room to swim around. In order to ensure the safety of the aquarium, he wants you to calculate the hydrostatic pressure on the bottom of the aquarium, the hydrostatic force on the bottom of the aquarium, and the hydrostatic force on one end of the aquarium. Alright, so we just kind of did calculating force at the bottom, right? We had that previous example. And so this is going to be pretty straightforward, except for one little caveat. This is in the imperial system. So the annoying thing about physics sometimes, you can change units. And so now we have to remember the rho, right, our density, times gravity, is going to be represented by this little lowercase delta here. And that is equal to 62.5 pounds per feet cubed. Alright, and our depth is going to be 3 feet. I almost said meters. Yep, that's not changing. Okay, so we just multiply our density, our density times our gravity times our depth. Alright, and that's going to be equal to 187.5 187.5 pounds per feet squared. Now we want to calculate the force. Easy, we just multiply it by the area. That's 5 times 2 is 10. and we have 1,875 pounds of force applied to the bottom of that aquarium. Alright, so how do we find the force applied to the side of the aquarium? Well, because our density is going to be changing as we change depths, we're going to need to do a little bit of calculus here. This is where the calculus finally comes in. And we're going to find the density for a tiny little sliver of area right here. Then we're going to add it to the next, we're going to add the forces, right? So we have a constant density. If we take this width to be small enough, or not a constant density, a constant pressure, sorry. If we take this width small enough, then we're gonna get a force. We're gonna add it to the force, the next force down, and keep on adding it all the way down this sidewall. Alright, so we're gonna set our depth equal to y. That's the first thing we're gonna do. And then we have our rectangle. And we are going to basically make that rectangle as skinny as we can. That's going to take the place of delta y. And that is 2 feet wide. Now, I wrote this as the area of I equal to the width of I times delta y, because in future problems this width will change. But we're lucky for this problem right here. It's just 2 feet. It's constant up and down here. These are parallel lines. And so it's just 2 times delta y. Alright, so now if we take the integral of that, evaluated from 3 to 0, we have our constant right here, 62.5, times our depth y, times 2, our width, times delta y, or dy. Alright, 62.5 times 2 pops out, 125, times the integral of 3 to 0 of our depth y times dy. That's just going to be equal to 125 times y squared over 2, evaluated from 3 to 0. Alright, the whole thing comes out to 562.5 pounds. And if you think about it, that's kind of consistent with at the bottom of this. Well, no, I guess you can't really compare it, but both sides are going to require some pretty strong glass panels. Alright. Our next problem here, problem number 9 from the book. Your grandfather is back. Impressed by your work with the fish tank, he asks you to build a dam for his trapezoidal river, and the dimensions are as follows. He wants you to explain how to find the hydrostatic pressure, or the hydrostatic force, against one side of the dam with a Riemann sum, and express that force as an integral and evaluate it. And so here's our dam. It doesn't have to be a dam, but the top is 4 feet long, the bottom is 8 feet long, and our water depth is 2 feet, and there's just a foot of air at the top here, and it's equilateral. So the first thing I want to do here, I don't really like this pocket of air up here, so I'm just going to use an old geometry formula, the length of the midsegment, to bring that down, so we're just dealing with what we want here, the water. So that's base 1 plus base 2 times 1/2, which is going to be equal to 6. Okay. So now that we have a trapezoid that we can work with, we need to figure out what the width is going to be, or what the length is going to be across, right? As we go down, what is this width going to be? And it's pretty easy here. We have nice numbers, right? 8 minus 6 is going to be 2. And so we know that the triangle on this end plus the triangle of this end has to be 2. And so each triangle has a width of 1, right? That's just kind of logical reasoning there. And what's the ratio of y to this width? Well, if we go down 2 feet, we go over 1 foot, right? So if we go down y distance, right, our width is just going to be equal to 1/2 y. Okay? Sure. So now we have 2 triangles, right? We remember. So our width in total is going to be equal to our original length up here, 6, plus y. Okay? Now, our grandfather asked for the Riemann sum on one side of that trapezoid, right? That's why I drew this little red line here. And so we're just going to take that width, divide it by 2. We're left with 3 plus 1/2 y. Okay, hopefully that isn't too confusing. Now, let's get back into the calculus. So the Riemann sum is going to be the sum of our constant, 62.5, times our depth, times our area. And so we just plug in kind of what we had before. We have 62.5, that's our constant, times our depth y, times 1/2 wi, remember that's changing now, times the delta y. Okay. So now, what's the integral? Well, it's 2 feet, 2 feet of depth, right? So we're going to evaluate it from 2 to 0, 62.5 times y, our depth, times w, our width, times dy. We just substitute in 6 plus y for our width there. Remember, that's the total width, not half of the width. Then we bring that 62.5 out, distribute the y times 6, y times y, that's y squared. And then this is a pretty easy integral. We just have 62.5 times 3y squared plus 1/3 y cubed, evaluated from 2 to 0. And in total, that comes out to 916 2/3 pounds applied to that dam that you're building for your grandfather's trapezoidal river. Alright, so for the second part of this little lesson here, we're going to focus on centers of mass. And these are also known as centroids in the mathematical world. And the classic example I have right here is the classic lever problem. And so back, I don't know how many years ago, Archimedes, the mathematician, came up with what's called the law of the lever. And it basically solves the problem here of where do we put this little red fulcrum to balance this board right here, this imaginary board. It's 10 meters long, so that both of these weights are balanced. And so essentially what we're going to do is we take the masses, right? We take all the masses on this board, and we multiply those masses by their x position. We sum them, and then we divide them by the sum of those masses. And that gives us our x moment. So what's important to realize is these numbers right here for the x-axis you don't have to start at the beginning here at 0. You can kind of put these wherever you want, and this will kind of show up in later problems. But for simplicity's sake, I just started at 0, and this goes, 10 meters long to the end here. But what is important is that these masses don't move. The masses are, at those locations. And there's also going to be an equal space between these points. It's just, it doesn't have to start at 0. Okay, so what do? This is pretty simple. We're just going to take that 4 kilogram mass, multiply it by 0, plus our 8 kilogram mass times 10, divided by the sum of the masses. 4 plus 8 is 12. And so we have 80 over 12 equals 6 2/3. And that's where we're going to put the fulcrum to balance these weights. And this kind of makes sense. You're going to have the fulcrum closer to the larger weight, pretty much in every case. And so what does this look like as a Riemann sum? Well, it's essentially the same thing. You can just make those little Riemann sum rectangles as thin as you want. Make n whatever you want. Just take the mass, multiply it by the x value, and then divide it by the sum of the masses. That gives you x bar. Okay, so on to the first problem. Problem 23. The masses m are located at the points P. Find the moments mx and my and the center mass of the system. So one thing that is a little complicated here is this notion of mx and my. Mx is basically the tendency for this point. Imagine this is a lever, right? And it weighs, 4, koala bears, whatever. You want to rotate it around the x-axis here. In order to do that, it's directly proportional to how far away this 4 is from the x-axis and how much it weighs. All right, this is in physics, this is the measure of torque, essentially. And so this, from mx, we're going to get the value of y, right? But it's important to remember that that's the measure for how easily it goes around the x-axis. And so you're going to see those interchangeably. It gets a little bit complicated, but as long as you remember mx around the x-axis and my around the y-axis, you should be good. So here are points, right, and here are the masses for each of those points. And to start off, we have to find my, okay? So the tendency for these points to rotate about the y-axis. What is that? That's just the sum of the masses times their x position, divided by the sum of their masses. Okay, so we have we have 4, and the x value of 2 right over here. We have 2 times the x value of -3 over here, and we have 4 times the x value of 3 over here. That's our numerator divided by the denominator, which is the sum of their masses, 14 over 10, equals x bar of 7 over 5. Okay, so then what's mx? The tendency to go around the x-axis. Well, that's just going to be this point over here, 4 times -3, plus 2 times the y value of 1, plus 4 times the y value of 5, divided by the sum of those masses again, works out to 10 over 10, with a nice y bar of 1. So where's that point? It's going to be right around here, 7 over 5, 1. And you can, think this kind of makes sense. The point's closer to the larger masses, and it's kind of in the middle here, balanced. Alright, so let's imagine you go to Home Depot, right? And you're buying a board, maybe you want to build a shed or something. I don't know why you'd build a shed, but just imagine. If you're trying to balance that board on your hand, right? You're going to start off trying to balance it in the middle. Not only in the middle of the board lengthwise, but also in the middle of the board widthwise, right? You're not going to start on the side. It would just fall down. And so this is important. And mathematically speaking, it's going to be, well, I'll get to that in a second. So how do we find the center of mass for a shape like this, right? At first, it's like, what the heck? This isn't a shape, This is just kind of a blob, and it can get into a blob, but there are ways to do this. So what we're going to do is we're going to take the Riemann sum, right? And we're going to find the center of each of those rectangles, right? Kind of represented by these points here. So these points are in the middle. I guess you could call this lengthwise, and they're in the middle widthwise, all right? And that's xi minus 1, or xi minus 1 plus xi, which is going to be equal to xi bar. And so essentially we're going to take the average of all these points going in this direction, and then we're also going to find the average going in this direction. And this is going to be, the mx and the my. All right. And when they intersect, that's going to give us our final point for the center of mass, or the centroid of this little blob here. And so the math gets a little bit complicated here, but it's really, well, it looks complicated. It's not that terrible, though. So xi, right, xi bar is going to give us the distance from the x-axis. So you can think this is xi going out a little bit for the first shape, then xi for the second shape, xi for the third shape, xi for the fourth shape, xi for the fifth shape, so on and so forth. Our little variable rho here also comes back for density, because these things have a uniform density, but we really don't have to think about it that much, because the rho is just going to cancel like immediately, so I wouldn't even put too much thought into that. And this f of x bar, that's going to be the height of the rectangle, right? So width times height times, the change in x is going to give us our my, right, and this is then represented as an integral from b to a of x times f of x dx. And then remember, we have to take my and divide that by the sum of the masses. Now the masses is just going to be equal to the area of this whole thing, technically times the density, but remember they just cancel. And so at the end of the day, we're going to have the integral from b to a of x times f of x dx all times 1 over the area, or just divided by the area. This is all for x bar. Y bar is similar, but not the same. So for y bar, we have to find the middle of this shape is really important. And so what do we do? Well, we take 1/2 of f of x. So, imagine this is f of x up here. We're going to go down halfway, right? We're going to take that, multiply that by f of xi, or f of x bar, times the change in x, again times the density. And this just works out to be 1/2 of f of x squared dx, evaluated from b to a. And again, you're dividing it by the masses. I also should have mentioned here, this f of x bar represents basically the value for each one of these rectangles. I misspoke when I said it was the middle for this top one, and actually for down here too. This is the value for each one of these rectangles, and that also kind of has to do with the mass, or it is the mass. Yeah. So moving on, we have the next problem, problem 29. Find the centroid, or the center of mass, of the region bounded by the given curves. So there's just a little Desmos graph. We have y equals x squared and x equals y squared. Just like that. And so how do we do this? Well, in the first problem, we had a pretty nice shape, right? We only had one line, right? We didn't have to worry about two curves here. So we could just go down to the x-axis and to the y-axis, and we didn't have to worry about subtracting area. Well, now, because we have a second line, we're going to subtract that area. And so we're just going to represent that as g of x. And essentially the formula is going to work the same way. We're just going to insert both functions into it, and we're just going to be subtracting that g of x area. And so, in order to find the area, we just take the integral. We know that these curves intersect at 0, 0, and 0, or not 0, 1, 1. And so we just take an integral, square root of x minus x squared. That comes out to 2/3 root x cubed minus 1/3 x cubed. And that comes out to 1/3. So that's the area of this shape. Next, we have to find the x bar. And so this looks complicated, but it's really not much worse than the area right up here. We're just taking the integral, or we have the formula from last time, taking the integral from b to a of f of x minus g of x. Sorry, f of x minus g of x times x. So you may be wondering, what is this x? Well, this x is going to be the distance from the y-axis, okay? Which is, you don't usually say x is the distance from the y-axis, but that's, what you're always measuring with x, right? And so that's equal to the integral from 1 to 0 of x times the square root of x minus x squared. That comes out to be x to the 3 over 2 minus x cubed. And then we take the integral of that. 2/5 root x to the 5th minus 1/4 x to the 4th, evaluated from 1 to 0. And that's pretty easy to plug in a 1 there. And then you, from that little evaluation in there, you get 3 over 20. And you're going to multiply that by 1 over the area of 1/3, which just comes out to be 9 over 20. Alright, so x bar is 9 over 20. What's y going to be? So if you reason, logically, you might be able to think, this is a pretty symmetrical shape. What does that mean? Well, we're going to see. Y bar, it's a little bit more complicated, but remember, it's the same formula we had before. 1 over a times the integral from b to a of 1/2. Remember, we have to find the middle of that rectangle, going up and down. We have to find the middle of it, of f of x squared minus g of x squared dx. And that's just going to be the integral from 1 to 0, 1/2 root x squared minus x squared squared. It comes out to 1/2 x minus the fourth x to the fourth dx. And then we come back down here, find the integral of that. 1/4 x squared minus 1/10 x to the fifth. And again, it's pretty nice. You can just plug in 1. You don't have to worry about the 0. Do some fractions. We have 10 over 40 minus 4 over 40. And we're going to divide that by the area. And so you can see, again, we have 1 over 1/3 times 3/20, which comes out to be 9/20. And so the center of mass for our shape here is going to be 9/20 x and 9/20 y. So thank you for watching. If you're able to follow all of this up until this point, then congratulations. I applaud you. And hopefully you'll have a good rest of this, school year and a good summer. Stay safe, everybody.